On September 15, 2017, a spacecraft the size of a school bus fell into Saturn at more than 111,000 kilometers per hour. Its antenna remained pointed toward Earth for as long as possible, sending one final stream of data across more than 1 billion kilometers of space. Then atmospheric drag overwhelmed it. The signal weakened, vanished, and Cassini was gone. But buried inside those last transmissions was a problem. The instruments had worked. The measurements were clean. The spacecraft had done exactly what it was designed to do. Yet the numbers did not fit the models scientists had spent decades building to explain Saturn's rings, atmosphere, and magnetic field. Cassini had spent nearly 2 decades traveling to and operating around Saturn. After launching in 1997, it crossed the solar system, arrived in 2004, and began one of the most productive planetary missions ever attempted. It completed 294 orbits, returned more than 450,000 images, flew past Titan 127 times, and passed close to Enceladus on 23 occasions. It watched storms spread around the planet, mapped the rings in astonishing detail, and transformed several small moons from points of light into complex worlds. By 2017, however, its fuel was running low. Mission controllers faced a serious problem. If Cassini became uncontrollable, it might eventually collide with Titan or Enceladus and carry traces of Earth biology onto a moon that could be habitable. NASA chose to destroy the spacecraft deliberately, protecting those environments for future exploration. But the ending became one final experiment. Cassini would dive through the unexplored gap, skim Saturn's atmosphere, measure gravity and magnetism at unprecedented range, and continue transmitting until the planet tore it apart. The mission was not being quietly switched off. It was being sent somewhere no engineer had originally dared to send it at the very end of its life. Cassini had entered a region no spacecraft had ever sampled directly, the narrow gap between Saturn's innermost ring and the top of its atmosphere. Engineers feared that space would be filled with dust, ice, and high-speed debris capable of destroying the spacecraft instantly. The first dive was so dangerous that Cassini pointed its large communications dish forward like a shield. Then the data arrived. The gap was almost empty. Particle detectors recorded far fewer impacts than expected. The region that had been imagined as a chaotic stream of dangerous debris was surprisingly clean, quiet, and structured. That was good news for the mission because it allowed Cassini to repeat the dive 22 times during its grand finale. Scientifically, however, it created a mystery. Material from the rings should have been drifting inward. Dust should have accumulated there. Yet something appeared to be sweeping the region clean. Electromagnetic forces may push charged grains away. Saturn's magnetic field may redirect some particles. But no model has completely explained why the gap remained so empty. And emptiness was only the first surprise. As Cassini crossed the region, its mass spectrometer sampled material falling from the rings into Saturn's upper atmosphere. Scientists expected mostly simple water ice. Instead, the instrument detected a chemical mixture far more complicated than anyone had predicted. There was water, but also complex organic compounds, silica nanoparticles, methane-related material, and heavier molecules that should have been difficult to form in such an environment. The space between the rings and atmosphere is extremely cold, nearly airless, and exposed to intense radiation. Those conditions are better at breaking complex molecules apart than assembling them, yet the molecules were there. It was like finding an intricate machine in the middle of an empty desert with no roads, footprints, or a workshop nearby. The evidence was real. The route by which it arrived was not obvious. This falling material is known as ring rain. Scientists had suspected it existed before Cassini, but the grand finale measured it directly. The flow was heavier, more chemically diverse, and more variable than earlier models suggested. Saturn's rings were not simply beautiful bands of passive ice. They were chemically active, constantly changing, and feeding material into the planet below. Some of the organics may form through sunlight-driven reactions on the surfaces of ring particles. Collisions may grind larger material into microscopic fragments. Magnetic forces may guide charged compounds inward. But when researchers tried to reproduce Cassini's measurements, the chemistry remained difficult to explain. Then Cassini encountered an even deeper problem. Every major planetary magnetic field is generated by moving electrically conducting fluid inside a planet. On Earth, molten iron circulates through the outer core. Inside Jupiter and Saturn, hydrogen is compressed so strongly that it behaves like a metal and carries electrical current. These internal motions create a magnetic field, but the field is normally tilted away from the planet's rotation axis. Earth's magnetic axis is offset by about 11 degrees. Jupiter's is tilted by roughly 10. Uranus and Neptune have far more extreme magnetic geometries. Saturn was already known to be different. Cassini's final orbits showed just how different. The spacecraft measured the magnetic axis as being aligned with Saturn's rotation axis, to within less than 1/100th of a degree. The alignment was so precise that it created a fundamental challenge for standard dynamo theory. A perfectly symmetrical magnetic field should not be able to sustain itself through ordinary fluid motion. Some asymmetry must exist. Something inside the planet should tilt or distort the field. Saturn appears almost perfectly aligned anyway. The planet is not breaking physics. More likely, scientists are missing an important layer of its interior. One idea proposes that a deep electrically conducting region smooths out the field before it reaches the surface. Another suggests that different layers rotate at slightly different speeds, hiding the asymmetry below the clouds. Neither explanation has been confirmed. This magnetic puzzle joins other mysteries Cassini left behind. Saturn radiates more energy than it receives from the sun. Helium may separate from hydrogen and fall through the interior like rain, releasing heat. But current models still struggle to match the observed output precisely. The giant hexagon around the North Pole has persisted for decades, yet simulations still cannot fully reproduce its stability, embedded vortices, and strange six-sided shape. Cassini spent 13 years transforming Saturn from a distant object into a detailed world, and somehow the planet became more mysterious with every answer. But the mission's most important discovery may not have been Saturn itself. It was Enceladus. Enceladus is a small moon, only about 500 kilometers wide, covered in bright ice. Before Cassini arrived, it looked like a frozen, inactive object. Then the spacecraft photographed enormous plumes erupting from long fractures near its south pole. Those cracks, known as tiger stripes, were spraying water vapor and ice into space. A moon this small should have frozen solid long ago. Yet gravitational forces from Saturn continuously squeeze and stretch its interior. That tidal flexing produces heat through friction, keeping a global ocean liquid beneath the ice. Cassini repeatedly flew through the plumes and sampled material coming directly from that hidden ocean. It found water, methane, carbon dioxide, organic compounds, and molecular hydrogen. The hydrogen was especially important. On Earth, molecular hydrogen can be produced when hot water interacts with rock on the seafloor. This process supports ecosystems around hydrothermal vents, where organisms survive without sunlight. Cassini's measurements suggested that similar reactions were happening inside Enceladus. The moon had liquid water, internal heat, active chemistry, and an energy source. By the end of the mission, scientists had identified 5 of the 6 major elements required for life as we know it: carbon, hydrogen, nitrogen, oxygen, and sulfur. One crucial element was missing. Phosphorus forms the backbone of DNA and RNA. It is essential to ATP, the molecule cells use to transfer energy. Without phosphorus, known biology cannot function. Cassini did not confirm it during the mission. The concentrations were too low for the original analysis methods. Then, 6 years after the spacecraft was destroyed, scientists returned to Cassini's archived data. Using improved laboratory measurements and more advanced analytical techniques, researchers re-examined ice grains captured from Enceladus's plumes. In 2023, they reported phosphate compounds at concentrations potentially far higher than those found in Earth's oceans. The final missing element had been there all along. Enceladus now had every major chemical ingredient associated with life, inside an ocean that was warm, active, and interacting with rock. That does not mean Cassini discovered life. Ingredients do not guarantee biology. A kitchen can contain flour, water, sugar, and heat without producing bread. Chemistry must organize itself into something capable of metabolism, reproduction, and evolution. No existing observation proves that has happened beneath Enceladus's ice. But the discovery changed the question. Before Cassini, scientists did not know whether Enceladus had an ocean. Then they found the ocean, the heat source, the hydrothermal chemistry, the organics, and finally phosphorus. The question is no longer whether the moon could support the basic chemistry of life. The question is whether that chemistry has already crossed the line into biology. James Webb later observed an enormous plume of water vapor extending far from Enceladus and feeding Saturn's broad E-ring. The moon was even more active than Cassini's close flybys had fully revealed, and that may be Cassini's greatest legacy. The spacecraft died in 2017, but its discoveries continued. Archived measurements produced major results years later because new tools allowed scientists to see patterns that had been invisible before. The raw data remained, waiting for better questions. There may be more hidden inside the archive now. Cassini's final moments contained no alien transmission and no secret message. What they contained was more scientifically powerful. Proof that Saturn's rings are chemically stranger than expected, that the planet's magnetic field challenges standard theory, and that a tiny moon contains an ocean with every known ingredient required for life. A future mission could fly through Enceladus's plumes with instruments far more sensitive than Cassini's, searching for amino acids, lipids, repeating molecular patterns, or other signs that chemistry has become biology. Cassini could not answer that final question. It made the question impossible to ignore. Its signal ended inside Saturn, but the conversation did not. The spacecraft disappeared in 91 seconds. The mysteries it uncovered may take generations to solve.